Hello again. In this video, we're going to talk about logarithmic differentiation. Now, logarithmic differentiation is a powerful tool that we can use to find the derivative of certain functions. And in this video, I'm going to go over a couple of examples where it would be useful to use logarithmic differentiation to find the derivative. Now, when you use logarithmic differentiation, you are going to be using three rules for logarithms that you should have seen before in college algebra. I want to remind you of them because we are going to be using them when we find derivatives using logarithmic differentiation. So the first one says that the natural log of x times y is the same as natural log of x plus the natural log of y. The second one says that the natural log of x divided by y is the natural log of x minus the natural log of y. So multiplication converts into addition here, and division converts into subtraction. And then one we've already talked about is the natural log of x raised to the z power is the same as z times the natural log of x. Okay, so let's look at an example where it would be useful to use logarithmic differentiation to find the derivative. So let's say you want to find the derivative of this function with respect to x. Now, if you were to do this directly without using logarithmic differentiation, it would be pretty difficult to find this derivative. First of all, you're going to have to use the quotient rule. And then within the quotient rule, when you take the derivative of the high function, you're going to have to use the product rule. And then within that product rule, I think you can see that you're going to have to use the chain rule because this first function is a composition of functions as well as the second one. So if you do this directly using the quotient rule, it can get pretty nasty, the algebra involved in it. So there's a way to avoid all of that. We're going to use logarithmic differentiation. And so here's the idea behind logarithmic differentiation. We're not going to find the derivative of this directly with respect to x. What we're going to do first is we're going to take the natural log of both sides of this equation. So that's going to give us natural log of y is equal to the natural log of this. And then I'm going to go ahead and write this square root as 3x minus 1 raised to the 1/2 power. Remember, you can always turn radicals into exponents. Just make sure that the bottom number is the index of the radical, which in this case is a 2. And then the top number is the power that it's being raised to. In this case, it's being raised to the first power. Okay, so you would write that as 3x minus 1 raised to the 1/2 power. Okay, all of that is divided by the x squared plus 4. Now, why are we doing this? Because we can take advantage of the properties that we just talked about for logarithms. We have division here, right? We're taking the natural log of two functions divided. So according to those properties, we can take the natural log of the top part, then subtract the natural log of the bottom part. Remember, when you say the natural log of a function divided by another one, it's the same as the natural log of the top function, minus the natural log of the bottom function. Okay, well, this is multiplication, so we can break this apart by saying, all right, that property says this is equal to the natural log of the first function plus the natural log of the second one. When you multiply here, it turns into addition. Okay, and then the other thing we can do is we can pull these exponents down in front and multiply them by the logarithms. Okay, and now after you've done this, then we're actually going to take the derivative of both sides of this equation with respect to x. In other words, we're going to find dy dx using implicit differentiation. Now, the reason this is better is because if you took the derivative right here, right off the bat, explicitly, you would have to use the quotient rule, which is a big mess in this case. But by using the properties of logarithms, we were able to turn multiplication into addition, and we were able to turn division into subtraction. And then these exponents turned into multiplication. And so it's just a lot easier to find the derivative of this as opposed to this. We don't have to worry about using the quotient rule or the product rule because we no longer have division and multiplication. Okay, so that's the reason we did this. Now, let's take the derivative of both sides with respect to x and find dy dx using implicit differentiation. Okay, so on this side, to find this derivative, we're going to have to use the chain rule because this is a composition of two functions. It's the natural log is the outer function, and the inner function is y. We're thinking of y as being a function of x. Okay, so we're going to get 1 over y, because that's the derivative of the outer function, and then times the derivative of the inner function with respect to x, and that's going to give us dy dx. Okay, again, we're using the chain rule. So this is the outer derivative times the inner derivative. The outer derivative comes from the fact that the derivative of ln of x is equal to 1 over x. But remember, you have to replace this with the inner function. So you substitute the y in for this x, and that's why it becomes 1 over y. Okay, and then of course the inner function is y, and we're taking the derivative of it with respect to x, and so that's your inner derivative, right? Dy dx. Okay, and then we can find the derivative of each of these individually. Okay, so let's take the derivative of the first one. You can pull the 4 outside the derivative operator since it's a constant. And then the same thing here. We're going to pull the 1/2 outside the derivative operator here. And then the final one is subtracting the derivative of this logarithm. Okay, so let's find the derivative of each of these. Okay, so on the left-hand side, we just still have 1 over y dy dx. And now the derivative of this logarithm here, right, let's start with this one. We're going to use the chain rule. Again, the inner function is x cubed minus 1, and the outer function is the natural log function. Okay, and so the derivative of the natural log function would be 1 over x, except we have to evaluate that at the inner function, so we replace this with x cubed minus 1. So it's actually 1 over x cubed minus 1. Okay, and then the derivative of the inner function would be 3x squared. Okay, so that's your outer derivative times your inner derivative. Then you do have this constant that sits in front. Okay, plus, all right, now the derivative of this one would be, again, you have to use the chain rule. The outer function is the natural log function. The inner function is 3x minus 1. Then the derivative of the natural log function is 1 over x, except you substitute this inner function in for the x. So it's actually 1 over 3x minus 1. And then multiply that by the inner derivative, which would be the derivative of this function, which is just 3. And then all of that gets multiplied by the 1/2. Okay, and then minus the derivative of this function. Again, you have to use the chain rule. Natural log is the outer derivative, x squared plus 4 is the inner derivative, or the inner function, sorry. Then the derivative of natural log is 1 over x, except you substitute x squared plus 4 in for the x. So it's actually 1 over x squared plus 4. And then the derivative of the inner function would be 2x. Okay, and then the last thing we have to do is we're going to solve for dy dx. Remember, we're trying to find the derivative of this function with respect to x, right? dy dx. So I actually have to multiply this y to the other side. So it's going to be y times all of this. And I'm going to clean this up a little bit. So on top here, you get 12x squared all over x cubed minus 1 plus 3 over 2 times 3x minus 1, and then minus 2x over x squared plus 4. And then the last thing we need to do is substitute for this y, because we really want our derivative in terms of x. And we know what y is. It's equal to this. So let's just substitute for that y. Okay, so dy dx is equal to y, which is this, times this piece. Okay, so that's the derivative of this function with respect to x. Now, admittedly, it's still fairly complicated, but it would be much more difficult to find this derivative using the quotient rule. So in this case, I think logarithmic differentiation is very useful. Okay, let's look at one more. Okay, you can also use logarithmic differentiation in cases where you have what are called tower functions. This is called a tower function because a tower function is a function that is raised to another function. So in this case, f of x is x, and it's being raised to another function, sine of x. Okay, that's known as a tower function. And anytime you want to find the derivative of a tower function, you can use logarithmic differentiation. Okay, so let's do that here. So let's take the natural log of both sides. Okay, and remember, we're trying to find dy dx. Okay, but we're going to do it implicitly, using implicit differentiation. So now we take the derivative of both sides with respect to x. Okay, well, why is logarithmic differentiation useful? Well, once I have this natural log on this side, I can take this exponent and multiply it in front. Okay, and then we'll find that derivative in a moment. I'll have to use the product rule to do that. Okay, we'll do that in a moment. But on this side, should be familiar. We did it in the previous problem. The derivative, you have to use the chain rule. So the outer function is natural log, and the inner function is y, which is a function of x. And so the derivative of the outer function, natural log function, is 1 over x. But then you have to evaluate that at the inner function, which is at y. So it's actually 1 over y. And then you take the derivative of the inner function with respect to x. And again, the inner function is y. So the derivative of it with respect to x is, of course, dy dx. Okay, now the only thing we have left to do here is to find the derivative over here. Again, we have to use the product rule. So we're going to go through the first times the derivative of the second. And of course, that derivative is just 1 over x. Plus the second times the derivative of the first. And remember, the derivative of sine is cosine. Okay, and again, we're going to have to multiply y to the other side because we really want to find dy dx. And I'm going to go ahead and write this as sine of x over x. And then just substitute for the y. The y is equal to x raised to the sine of x. Okay, so that's the derivative of this tower function with respect to x. It's equal to this. Now, there is another way to do this problem. You, of course, can use logarithmic differentiation to find this derivative of this tower function. But when you have a tower function, you can also use this little trick. So I'm going to show you a second way of finding this. Remember, earlier in this section, we talked about this property that e raised to the ln of x is the same as x, since e and ln are inverse functions of each other. So we can take advantage of this property. If this is true, then if I take e raised to the ln of x raised to the sine of x, then that would be the same as x raised to the sine of x. Okay, and so what we're going to do is we're going to find dy dx. Not directly, not written in this form. We're going to write it like this. Now, the reason that's useful is because now that you have this natural log in front, you can pull this exponent down and multiply the exponent by the natural log. And so what it boils down to at this point is you're now finding the derivative of an exponential function. The base is e, and this is the power that it's being raised to. So this is really a composition of those two functions. Again, the inner function would be sine of x times ln of x, and the outer function would be the exponential function with the base of e. Okay, so let's find this using the chain rule. Okay, of course, u is going to be this inner function. Then the outer function would then be e to the u. Okay, and so dy du would be the derivative of this with respect to u, and that's just e to the u. And of course, you can replace the u here u is equal to this. So you just get e raised to sine of x times ln of x. Okay, and now we have to find du dx, which is the derivative of this function. And notice again, you're going to have to use the product rule. We already did that, right? We found that derivative here, so it's going to end up being this using the product rule. So it's sine of x over x plus natural log of x times cosine of x. Okay, and then when you multiply those together, the outer derivative times the inner derivative, you get the derivative of this composition. Okay, so the outer derivative times the inner derivative. Okay, and then we're supposed to get the same answer regardless of which way we do it. So you can see that the difference lies in here. These are really equal to each other because you can manipulate this back into this form. So the way you would do that is you would bring this sine of x back up as an exponent. Again, you're allowed to do that because that's a property of logarithms, right? You can pull the exponent down and multiply it in front. You can also take this and move it up as an exponent. Okay. And what does that do for us? Well, these are inverse functions of each other. Right? Remember, e raised to the ln of x raised to the sine of x is the same as x raised to the sine of x. So you get the same answer. Okay, so it doesn't matter which way you do it. If you prefer logarithmic differentiation, then you can do it this way. Or if you prefer using this little trick that we talked about earlier, you can turn this into an exponential function and then find the derivative of it using the chain rule. Okay, but it doesn't matter. You get the same answer either way. I will say this. When you have a tower function like this, you have an option, right? You can do it one way or the other. But when you have a function that looks like this, and you're trying to avoid using the quotient rule, then it would probably be better to do this using logarithmic differentiation, although I don't think it matters, actually. You would take this and write it as e raised to the ln of this function. And then you could unravel all of this. Now that you have a logarithm in front of it, you can unravel this using all the rules that we have for logarithms and get it to be written like this. Okay? Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.